Hello guys, I'm Tanish Sharma, course MTech IT, roll number IT2K1963 from International Institute of Professional Studies, guided by Dr. Shaligram Sir. So, the first question is analysis the time complexity of the quick sort algorithm in average case and provide a step-by-step explanation of the sorting process. Quicksort is a widely used sorting algorithm that uses a divide and conquer approach to sort elements of an array. It is considered one of the fastest sorting algorithm with an average time complexity of O of n into log n and a worst case complexity of O of n power 2. Time complexity analysis in average case. In the average case, quicksort exhibits the time complexity of O of n log n where n is the number of elements in the array. This is considered efficient and makes quicksort one of the fastest sorting algorithm in practice. Here is the step-by-step explanation of how the quicksort algorithm works. Choose a pivot. Select a pivot element from the array. The choice of pivot can impact the performance of the algorithm and different strategies can be used. Example, choosing the first, last and middle element. Partitioning. Rearrange the array in such way that all elements less than the pivot are placed before it and all the elements greater than the pivot are placed after it. This step ensures that the pivot element is in its correct sorting position. Recursive calls. Recursively apply the above two steps to the subarrays of the left and right of the pivot. This means repeating the partitioning step each subarray until the entire array is sorted. The recursion ends when the subarrays contain only one element or are empty combined. Since the elements are rearranged in place during the partition step, no additional combining or merging is required. The next, repeat until sorted. Repeat step 1/4 until the entire array is sorted. At each step, the pivot element is placed in its final sorted position, reducing the size of subarrays that need to be sorted. The time complexity of quick sort in the average case in O of n log n. This is because the array divided into subarrays of roughly equal size and the pivot element is chosen randomly, which means that on average it will be close to the median of the array. The second question is critically evaluate Strassen's matrix multiplication algorithm and compares its time complexity with the traditional matrix multiplication method. The answer is Strassen matrix multiplication algorithm is an algorithm that aims to reduce the time complexity of matrix multiplication compared to the traditional method. It achieves this by using a recursive approach and dividing and matrices into smaller submatrices. However, while Strassen's algorithm provides a theoretical improvement in the time complexity, it has practical limitations and is not always faster than the traditional method. Here's critical evaluation of Strassen's matrix multiplication algorithm. The advantages of Strassen's algorithm reduces time complexity. Strassen algorithm has the time complexity of O of n power log to 7, which is approximately O of n power 2.81. This is an improvement of over the traditional matrix multiplication, which has the time complexity of O of n power 3. Using the straightforward approach, efficient for large matrices, Strassen's algorithm is particularly effective when dealing with large matrices, as the reduction in the number of multiplication can significantly reduce the overall computation time. The disadvantage of limitation of Strassen's law overhead. Strassen's algorithm introduces additional overhead due to recursive calls and matrix additions. This overhead can offset of the benefit gained from reducing the number of multiplication, especially for smaller matrix. As the result, the traditional method can be faster for a small medium-sized matrices. Increased memory uses. Strassen's algorithm requires additional memory to store the submatrices creating during the recursive process. This increased memory uses can be problematic for large matrices as it may exceed the available memory capacity. Compare the traditional matrix multiplication algorithm and iteration algorithm are both used to multiply two matrices, but they use different approaches to achieve this goal. The traditional matrix multiplication algorithm is based on the definition of matrix multiplication, which involves multiplying the elements of the row in the first matrix with the corresponding elements of a column in the second matrix and adding up the products. This process is repeated for all rows and columns in the matrices of often the final project. The time complexity of the traditional method is O of n power 3 when n is the size of the matrices being multiplied. On the other hand, Estressen's algorithm uses a divide and conquer approach to multiply matrices. The algorithm works by recursively dividing the matrix into smaller submatrices, performing a set of mathematical operation of this submatrix and then combining the result of obtain the final product. The time complexity of extraction algorithm is O of n power log 2 7, which of approximately O of n power 2.81. The question number 3. Evaluate Prim's algorithm for finding the minimal spanning tree and provide a real world scenario where it can be applied. The answer is Prince algorithm is the popular algorithm for finding the minimum spanning tree of a connected weighted graph. The algorithm works starting at with the single vertex and gradually adding edges from a tree that spans all the vertices in the graph. At each step, the algorithm chooses the edge with the minimum weight that connects a vertex in the tree to a vertex outside the tree. One of the main advantage of Prim's algorithm is that it is guaranteed to find the minimum spanning tree of the graph. This means that the tree formed by the algorithm has the smallest total weight of the all possible spanning trees of the graph. In addition, the algorithm has a time complexity of O of E log V, where E is the number of edges in the graph and V is the number of vertices. This makes the algorithm efficient for large graphs. Advantage of Prince algorithm efficiency. Prince algorithm has a time complexity of O on V power 2 with an adjacency matrix representation and O of E log V with the adjacency listed representation where V is the number of vertices and E is the number of edges. This makes it efficient for dense graphs and relatively efficient for sparse graphs. Guarantee minimum tree spanning tree. Prim's algorithm guaranteed the construction of a minimum spanning tree. The resulting tree has the minimum total weight among all possible spanning trees in a graph, ensuring optimal connectivity. The third one is suitable for distributed system. Prim's algorithm is well suited for distributed system as it can be easily parallelized. Each node can independently compute the minimum weight edge connected to it, making it efficient for distributed implementation. Real world scenario. Telecommunication network planning, a real world scenario where Prim's algorithm can applied in this telecommunication network planning. Consider a telecommunications company that wants to establish a network infrastructure connecting multiple cities with the least amount of cable users. These cities can be represented as vertices and the cables required to connect them. They can represent as weighted edges. The question number 4. Derive the time complexity of iterative and recursive version of Fibonacci function and compare their efficiency. Answer. To derive the time complexity of the iterative and recursive version of the Fibonacci function, let's analyze each approach separately. Iterative Fibonacci function. The iterative version of the Fibonacci function calculates the Fibonacci sequence iterate, iteratively uses a loop. Here's the code. The time complexity of the iterative Fibonacci function is O of n. Since it performs a loop that runs times where n is the input number, each iteration involves a constant amount of work. So the time complexity grows linearly with n. Recursive Fibonacci function. The recursive function version of the Fibonacci function calculates the Fibonacci sequence by recursively calling itself. Here's the code. The time complexity of the recursive Fibonacci function can be derived using a recurrence relation. Let T of n represent the time complexity for calculating the nth Fibonacci number. Efficiency comparison. The iterative Fibonacci function is the significantly more efficient than the recursive version, while the iterative approach has a linear time complexity of figure of n. The recursive approach has an exponential time complexity of figure of 2 power n. As the result, the recursive function becomes increasingly inefficient as n grows larger. The inefficiency of the recursive Fibonacci function is primarily due to the repeated calculations of the same subproblems, resulting in redundant work. In contrast, the iterative function avoids redundant calculations and calculates the Fibonacci number in a bottom up manner, leading to better performance. The question number 6. Explain chain matrix multiplication with the suitable example and discuss its practical applications. Evaluate the time complexity of chain matrix multiplication. So, the matrix multiplication refers to the process of multiplying several matrices together in a chain or sequence. The order of multiplication matters, and the goal is to minimize the number of scalar multiplication needed to the compute the final result. For example, consider the multiplication of three matrices A, B, and C, where A has dimension 10 into 5, B has dimension 5 into 20, and C has dimensions 20 into 2. If we were to simply compute the matrix product ABC using the standard matrix multiplication algorithm, we would to need to perform this line scalar multiplication. However, if we rearrange the order of multiplication to A, B, C, we can reduce the number of scalar multiplications needed. The intermediate result of multiplication of A and B has dimension 10 into 20, so the final multiplication with C requires only 10 into 20 into 2 plus 10 into 5 into 2 is equal 400 plus 100 is equal 500 scalar multiplication. This is the significant improvement over the previous approach. The time complexity of chain matrix multiplication depends on the order in which the matrices are multiplied. If we consider a chain of n matrices with dimensions this one, where the dimensions are such that the matrices product is well defined, then the number of scalar multiplications needed to compute the product using the standard matrix multiplication algorithm is given by the following recurrence relation. The time complexity of computing m ioj for all ij and 1 and using dynamic programming techniques is Vigo of n power 3, which involves filling in a table of size n into n. Once we have computed the table of minimum scalar multiplication, we can use it to determine the optimal order of multiplication by tracking back through the table. The time complexity of this step is Vigo of n. Therefore, the overall time complexity of chain matrix multiplication using dynamic programming techniques is Vigo of n power 3 plus n is equal Vigo of n power 3. The question number 5. Write non-deterministic search and non-deterministic sort algorithm. The answer is non-deterministic search algorithm. Non-deterministic search algorithm do not follow a specific deterministic path but explore multiple possible paths simultaneously with the hope of finding a solution. One such algorithm is non deterministic depth first search. NDFS. There is a code for NDFS. Here's the pseudocode for this. Non-deterministic sort algorithm. Non-deterministic sort algorithm are based on the concept of non-deterministic computation where multiple possible outcomes are explored at the same time. However, it's important to note and non-deterministic sorting algorithms do not exist in practice since sorting is typically a well-defined and deterministic problem. Nevertheless, I can provide a simple example of non-deterministic sorting algorithm called non-deterministic bubble sort for illustrative purpose. There is the pseudo code of bubble sort with non-deterministic function. Question number 5. Analyze and compare the class P, NP, and NP hard and NP complete problem and provide the example of each. Discuss their significance in computer science and their potential in real world application. The answer is in computer science, the complexity classes P, NP, NP hard, and NP complete play a fundamental role in understanding the difficulty of computational problems. Here's an analysis and comparison of these complexity classes along with example and their significance in computer science and real world applications. Class polynomial time. A problem is in class P if there exists an algorithm that can solve it in polynomial time, meaning the running time of the algorithm is bounded by a polynomial function of the problem size. Significance. The problem is class P have efficient algorithm that can solve them in a responsible amount of the time of large inputs. They are considered computationally treatable and form the basis for many practical applications in areas like data processing, optimization, algorithm design. Class Class NP non-deterministic polynomial time. A problem is in class NP if a proposed solution can be verified in polynomial time. While NP stands for non-deterministic polynomial, it does not necessarily mean that problems in NP can be solved in the polynomial time. Significance. Problems in NP represent a class of problems where a proposed solution can be quickly verified even though finding the solution may be computationally challenging. NP problems offer great interest in computer science as they include many real world optimization, decision, and scheduling problems. Solving NP problems efficiently is a significant open question in computer science with implications for cryptography, optimization, and artificial intelligence. NP hard non-deterministic polynomial time hard. A problem is NP hard if it list as hard as the hardest problem in a class NP. In other words, an NP hard problem is difficult as or harder than any problem in NP. Significance. NP hard problem represent a set of computationally challenging problems that do not necessarily belong the class NP. Solving NP hard problems optimally for all inputs is considered intractable and efficient algorithm for NP hard problems are the topic of active research. Many real world optimization problem can be modeled as NP hard problems and developing approximation algorithms and heuristics for these problems is crucial. NP complete non-deterministic polynomial time complete. A problem is NP complete if it is both in class NP and is NP hard. NP complete problem are the hardest problem in the NP and a solution of any NP complete problem would imply a solution to all NP problems. Example of NP complete problems include the Boolean satisfiability problem, SAT, the knapsack problem, and the traveling salesman problem. TSP. Significance NP complete problems are the utmost importance is computer science as they represent the most challenging problem in class NP. Thank you, sir.